Welcome to Math Mini Academy. In this lecture, we are going to discuss the linear algebra questions which are asked in June 2007. The first question of part B is, let A be a 4 by 4 matrix. So A is given to be a 4 by 4 matrix and the null space of A is defined as this one. That is, null space of A is equal to the collection of the points from R4 such that it is satisfying two conditions. The first one is x plus y plus z is equal to 0 and the second condition is x plus y plus w equals 0. These are the conditions. Here if you just see, we can write this as a set spanned by a different set of elements, for which you just put x is equal to 1 and y is equal to 0 in it, and you would see 1. When I put x is equal to 1 and y is equal to 0, I would get z is equal to minus 1, right? And similarly, I would get minus 1 for w as well, right? Okay, then if I put x is equal to 0 and y is equal to 1 in it, then what do I have? I would have 0, 1, minus 1, 1. Okay, so this null space can be spanned by these two entries. If you are able to get this ideology, you may think in this way. A is a mapping which can be treated from R4 to R4, right? So we can treat this as a linear transformation. Now null space of A is a subset of what? The domain, right? So this is basically a vector space. Null space of A is a subspace of R4. Now we are interested in the dimension of null space of A. This is dimension of R4 minus number of linear restrictions, linear independent restrictions, right? So how many linear independent restrictions are imposed here? Two linear restrictions are imposed. Therefore 4 minus 2, which is 2. By rank nullity theorem, what do we have? Rank of A plus nullity of A equals 4. Nullity of A is proved to be 2. Therefore rank of A is 4 minus 2, which is 2. Rank of A is nothing but the dimension of column space. Either you can have it as a column space or this is dimension of row space. Okay, so the dimension of column space of A is 2. Okay, that is what. Here in option 4 they were asking about the basis for n of A. That is why here I have given you the idea to find out the basis elements which generate n of A, for which what I have it. Since we have two restrictions, I have put in both the restrictions I have x and y. That is why I have put x is equal to 1 and y is equal to 0 at first instance, and then x is equal to 0 and y is equal to 1 in the second instance, and I get the value of z and w, with which I have written out the basis entries. Okay, so the right answer to this question is option 2. That is the dimension of column space of A is 2. Moving to the next question, here we have A and B are invertible matrices such that AB is equal to minus BA. We have seen one such question in one of the previous year itself. That is quite simple, right? Since A and B are invertible matrices, A inverse and B inverse exists. If these two things exist, you can multiply A inverse and B inverse to them, like AB A inverse is equal to minus B A inverse. When I multiply A inverse, and this is what I am getting. When I multiply B inverse, I would get AB B inverse is equal to minus B A B inverse. So this is AB A inverse is equal to minus B. And here what would I get? A is equal to minus I am taking to the left hand side. So A is equal to BA B inverse. This is what we would have. So from this what we get? Bn minus B are similar. And here we get minus A and A are similar. if we have similar matrices, then their trace as well as the determinant are equal. Since the question is, since the options are about trace, trace of B is same as that of trace of minus B, which tells us that trace of B is 0. In a similar way, we get trace of A is equal to 0. Option 1 claims the same. Moving to the next question. Here it is given that A is a self-adjoint n by n self-adjoint matrix with eigenvalues, and norm of any vector x is given in this fashion, where x is a vector in Cn. Okay, and if P of A is defined in this form, then what is the supremum of this quantity? Okay, so there is a typographical here. We will have to find out this supremum value. When do we say A is self-adjoint? Self-adjoint means this A is same as that of A star. Okay. Here, what is the underlying field? Which is the set of complex numbers. And we know every self-adjoint operator is normal. Is normal. Okay. By normal, what do we mean? That is t star is equal to t star t. Since t is same as that of t star, this is trivial, right? And we have a result that says that every normal operator is diagonalizable and there exists a basis. I name that basis as beta, which is u1, u2, etc. un, such that the matrix of T with respect to this beta is diagonal, and moreover this beta, the collection beta, is an orthonormal set. What do we mean by an orthonormal set? The entries of this beta are mutually orthogonal and each vector is of length 1, right? So with which we are proceeding. We have selected this u1, u2, etc. un as an orthonormal basis consisting of eigenvectors. So basically what we are assuming is that the collection un bn orthonormal basis consisting of eigenvectors, that is aui equals lambda ui, where I runs from 1 to n. Okay, let us choose an element x which is a vector in Cn. Then how does the norm is defined? Norm x2 is defined in a usual sense, that absolute of x1 whole square etc. till absolute of xn whole square. Okay, and we are interested in finding the supremum of square root of norm pa x, right? That is what we'll have to find. Okay, here let x be an element of Cn such that this norm is 1. Okay, then this x can be written as alpha 1 un alpha 2 u2 till alpha n un. Why so? Because we have considered the set un, u2, etc. un is an orthonormal basis which consists of eigenvectors. That doesn't matter here, but this is an orthonormal basis of Cn. Hence every element in Cn can be written in this fashion. Okay, and it is said that this norm x2 is 1. So this may be written as x comma u1 multiplied with un. then x comma u2 multiplied with u2, etc. till x comma un multiplied with un. So this is the way in which you can find the values of alpha 1, alpha 2, etc. alpha n. Okay, this clearly tells you that square root of absolute of alpha 1 square, etc. till alpha n square is 1. Now let us find out what is p of a x. First of all, let us find out what is p of a x. It is what? P of a is given as a naught I etc. a1 a plus etc. till an a power n. Okay, which is to be multiplied with alpha 1 u1, alpha 2 u2 till alpha n un. So when you multiply it, what are you going to get? A naught. Okay, I'll have this a naught alpha 1 u1, then a naught alpha 2 u2 till a naught alpha n un, then a1 alpha 1 au1. Okay, the scalars I have taken to the left and the remaining I have this way, then a1 alpha 2 au2, etc. till a1 alpha n aun. Okay, then plus etc. till what we'll have, an alpha 1 a power n u1, etc. till an alpha 1 a power an alpha n a power n un. Okay, so from this you just substitute the fact that here we have this aui is equal to lambda ui, right? So when you have this aui equals lambda ui, this clearly implies that an ui equals lambda power n ui. Okay, I am going to directly substitute in the place of au1. I am going to substitute it as lambda u1. Okay, and here I will have lambda u2, and here I will have lambda un. In a similar way, here I will have lambda power n u1, etc. till lambda power n un. So I will have these quantities. Now I can very well club this. If I take alpha 1 as a common quantity, then I will have what? So just look at the first entry, first element in all the lines. So if I take alpha 1 as a common quantity, then I will have a naught u1 plus a1 lambda u1, etc. till an lambda power n u1. Am I right? From this I can very well take this u1 outside. In a similar way, I will have alpha 2 a naught a1 lambda, okay, etc. till an lambda power n u2. In this fashion, I will get till alpha n a naught a1 lambda, etc. till an lambda power n un. Okay, if I now evaluate the norm of p of a x 2, what am I going to get? I would get norm of alpha 1 p of lambda u1. Okay, alpha 2, just a minute. So actually corresponding to each vector, we will have a corresponding eigenvalue, right? So I just made this mistake. So here we will have lambda 1, lambda 2, lambda n. Here also lambda 1, lambda n. So this is what we are going to have, alpha 2 p of lambda 2 u2. Okay, actually here lambda 1, then this will have lambda 2, and this will have lambda n. Actually the thing is that it is an orthonormal basis of eigenvectors. All these things are right. For each eigenvector, there is a unique eigenvalue corresponding to it. That is what we are denoting by lambda I. If if ui is the specific eigen vector that we are dealing, then corresponding to it there is an eigen value that we denoted by lambda I. Okay, so now you must have understood, I hope. Then alpha n p of lambda n un. So this is what we have. Okay, if we just expand it, what are we going to have? We will have under root alpha 1 square, then what? P of lambda 1 whole square, and when you take norm of this u1, that becomes 1 since it is an orthonormal 1, right? So we'll have till alpha n square p of lambda n absolute of p of lambda n square, right? So this is what we have. And if you define m to be the maximum of absolute of p of lambda I square, where I runs from 1 to n, okay, then what we are going to have is absolute norm of p of a x 2 is smaller than or equals, actually this would be this is the maximum one, so we just replace it and we would have m times of, in all the place of this lambda 1 and all, we shall replace with, actually this will be less than or equals, okay, less than or equals under root alpha 1 square m, okay. So actually not this one, we'll have this as m, so that it is m square, then etc till alpha n square m square. And when you take this m outside, what are you going to get? You would get norm of p of a x2 is less than or equals m times of whatsoever the quantity is left, that is equal to 1. So this is what we are going to have. So what is this m? This is nothing but the maximum of this quantity, isn't it? So if this is so, then supremum of norm x2 is equal to 1 of this p of a x2 is less than or equals maximum of this absolute of p of lambda I, where I run from 1 to n. So we have proved the one way. In order to prove the other way, you just observe this absolute of p of lambda I whole square is smaller than or equals norm of p of a x, okay, from which what we have is norm of p of a x2 is bigger than or equals norm of p of a ui, okay. You may have it as u1, any ui, okay, for some I between 1 to n, okay, with which what can we say? So norm of this quantity is what? P of a. So this may be written as this is p of lambda I ui, and this is nothing but absolute of p of lambda I into norm ui, and we are left with p of lambda I, absolute of p of lambda I. Then take supremum norm 2 equals 1, this p of a x2 is bigger than or equals maximum of this p of lambda I, where I run from 1 to n. Combining these two things, we will get the answer, that is our option 2. Okay, this may be this may be a quite theoretical ideology, but when you have the complete idea of norm and everything, then proving this is quite easy. Okay, now actually I don't say it is quite easy, but we'll have to come in a flow, right? Or you may just what to say, there is no shortcut idea or anything like that for this kind of problems. We'll have to work it in a proper way. So first of all, the ideologies that we must have is, what do we mean by a self-adjoint matrix? So for every matrix we can associate an operator to it, and we must know the property of a self-adjoint operator, that every self-adjoint operator is a normal operator, and for normal operator we can always diagonalize it with the help of an orthonormal basis. So what can we play with orthonormal basis, and that is what we have done, right? Okay, now moving to the next question. Here it is given that a matrix is given, okay, and some expression is given, and we'll have to find out the values of ABC in that expression. Okay, if this is your matrix, then what is your characteristic polynomial? It is simply determinant of 1 minus x 0 2 1 minus 2 minus x 0 0 0 minus 3 minus x, right? It is 1 minus x times of minus 2 minus x minus 3 minus x minus 0, and then minus 0 of something plus 2 times of 0. So finally what we end up is 1 minus x. If you take minus from this and this, that becomes plus. So 2 plus x and 3 plus x. So it is 1 minus x times of x square plus 5x plus 6, and multiply this inside x square plus 5x plus 6 minus x cube minus 5x square minus 6x. So as a whole, this becomes minus x cube minus 4x square minus x plus 6 equal to 0. So this may also be written as x cube plus 4x squared plus x minus 6 equals 0. So from which what we get is 6 equals x cube plus 4x square plus x. So this is the characteristic equation. Actually from this stage we get the characteristic equation. For simplicity purpose, and actually not for simplicity purpose, in order to evaluate this problem I have written this one. Okay, by Cayley-Hamilton theorem, every square matrix satisfies its own characteristic equation. So what I get is 6i equals a cube plus 4a square plus a. If you multiply a inverse with this, what you are going to have is 6a inverse is a square plus 4a plus identity. If you just compare this one with the given thing, you would get a is equal to 1, b is equal to 4, and c is equal to 1. That is our last option. Moving to the next question. Here a matrix is given and we are asked to evaluate the eigenvalues of A. So in order to evaluate the eigenvalues, the very trivial way that we all know is to find the characteristic equation and solving it. Okay, that is one way. Here I am going to make use of the properties of eigenvalues to verify or evaluate this problem. Okay, so it is a matrix is given from which determinant of A is what? It is 1 times of 6 minus 25 minus 1 times of minus 3 minus 10 plus 2 times of 5 plus 4. So this is minus 19 plus 13 plus 18. Okay, which is 12. Okay, and what is trace of A? It is 1 plus of minus 2 plus of minus 3, which is 4. So trace of A is trace of A is minus 4 and determinant of A is 12. We know that if lambda 1, lambda 2, lambda 3 are eigenvalues of A, then determinant of A is product of the eigenvalues, and trace of A is the sum of the eigenvalues. Okay, so first of all let us verify the sum. If we add whatsoever is given, actually this is there is a typographical, it is 2. Okay, if we add all the eigenvalues we must get 4. If we add all the things in the first option, yes, we are getting minus 4. This has the chance. Okay, if we add all the values in option 2, it is not equal to minus 4, though that loses its chance. Okay, and if we add here, this plus 13 and minus 13 gets cancelled and we have minus 4 plus 4 and minus 4. Yeah, it has a chance. And if when we move to the option 4, it has 4 minus 2. This 2 root 7 and minus 2 root 7 gets cancelled. This also is not equal to 4. So option 2 and 4 loses their chance just by checking the trace property. Okay. Now let us check the determinant one. So minus 4, 3 minus 3. What do we get? We get 36, which is not equal to 12. Okay. 4 multiplied with minus 4 plus root 13 and minus 4 minus root 13, which is 4 times of, this is in the form of a plus b into a minus b, therefore minus 4 square minus under root 13 square, which is 4 times of 16 minus 13. So 4 into 3, which is 12. It satisfies the given property, therefore option 3 is the right one. Okay, so we have covered the part B questions. Now we are stepping into part C questions. Here it is given that we are asked to consider the vector space V of real polynomials of degree less than or equal to n. Now we will have to fix a distinct real number a0 through ak. Okay, so with which what should we do? And they have defined a maximum of the polynomial evaluated at the points a0, a1, etc. till ak. They are saying that maximum of this quantity defines a norm. Then which of the following are true? Okay, polynomial of degree less than or equal to n. So it is given that, okay, p of x may be written as a0 plus a1x, a2x squared, etc. till an x power n. Okay, so if it is a vector space, all this stuff is fine. If we are able to get all the roots of this polynomial in real field itself, then what do we have? Then we must have x minus alpha 1 into x minus alpha 2, etc. till x minus alpha n, since it can have at most n roots. Okay, here the alpha j are roots of p of x. Okay, if they are repeated, I am counting it twice. That is what I have done here. Okay, why have I written here? That is what we are going to check. Okay, now clearly they have said that this defines a norm. If it has to define a norm, then what should be the case? We must have all the 4 properties of a norm. That is just a minute, I'll write that in different color. Absolute of x has to be greater than or equal to 0 for all x in V, and norm of x has to be equal to 0 if and only if the norm vector itself is 0. Then norm of alpha x is absolute of alpha into norm x for all alpha in the field, and the triangle inequality. These are the 4 conditions that we should have if this quantity defines a norm. Okay, so here with which we are going to examine, as usual we will take the second one. If it defines a norm, then maximum of this p of absolute of this p of aj, where j runs from 0 to k, if it has to be equal to 0, then we must have our polynomial itself is 0. Okay, it means what? Maximum of absolute of p of a0, p of a1 till p of ak. If this has to be 0, then this must be the case. Okay, maximum of, okay, we know that absolute of any quantity is a non-negative quantity. Maximum of some non-negative quantity is equal to 0, which means what? Each quantity has to be equal to 0, right? If each quantity is equal to 0, then this is true. Okay, this is what. If this is so, then what can we say? P of absolute of P of A naught is 0, which means P of A naught is 0. If P of A naught is 0, then I can write my P of X as X minus A naught into some Q naught of X. Okay, P of A1 is 0. If I combine these two things, I would have P of X is X minus A naught, X minus A1, then some Q1 of X. Okay, when I proceed this way till ak is equal to 0, then what am I going to have? Then I must have x minus a naught, x minus a1 till x minus ak into some q of x. Only then my p of x can be equal to 0. Okay, let us say that this suppose this degree of q of x is bigger than or equals 1. Then what happens? My p of x has a degree which is bigger than or equals k plus 1. Actually k plus 2. Am I right? So here we have k plus 1 factors and we are saying that this degree is bigger than or equals k plus 1. Therefore n has to be greater than or equals k plus 2. This is what we are getting. Is this anyway feasible? No. Right? The thing is that okay, if p of x has to be a 0 polynomial, then it must not have any root. Like 0 has to be there as a root. Okay, so assuming degree of q of x is bigger than or equals 1 is not at all possible. Hence, it will not form a norm when your degree of q of x is bigger than 1, which means when if this is so, this means what? Your k is less than n, right? This will be the case. Your k will be less than n. If k is less than n, then whatsoever is given, this maximum of this quantity will not form a norm. If your k is bigger than or equals n, then it is going to be true. So option 2 is the right one. And if you check for other things, it will not be there. And the simple logic is that you have, okay, this is some theoretical ideologies. Let me give you a shortcut way as well. Here, if p of x is a polynomial, then it must have n roots. Okay, and you are saying that the points you are defining maximum of something. Here, if you evaluate these points at n places or more than n places, and if you are getting that to be equal to 0, then your polynomial can be a 0 polynomial. So the thing is that your k, actually this k, 0 from k, this k has to be equal to n or greater than n. Only then it will form a norm. Okay, because it must have minimum of n linearly independent factors. Okay, minimum of n linearly independent factors. So the condition that you are imposing has to be either equal to n or bigger than n. That is what option 2 says, right? In no other option it is said. That is why we are going for it. And in option 3 and 4 they have given if that is satisfied, and in option 1 and 2 they have said only if. If means suppose that is happening, that k is bigger than or equals n plus 1 or k plus 1 is smaller than n is happening. Suppose that is happening, then your maximum so and so will define a norm. That is what they are saying. If that is not happening, I don't bother. It may be a norm or may not be a norm. That is the case. If is specified, that is the case. Only if means this has to happen in order for the maximum of that quantity to become a norm. That is what it means. Okay. Moving to the next question. Here we have V is a vector space of polynomials of degree at most 3 in the variable x. So V is basically something of this form, where all this Aj are real. Okay, J running from 0 to 3. And T is a differentiation operator, that is the linear transformation to be considered here, and we'll have to check what are the things that are going to happen. So for option 1, 2 and 3 nothing is specified, only for option 4 some basis is prescribed. We will go with the standard basis in order to evaluate the options 1, 2 and 3. This is the standard basis, right? And what is T of 1? Derivative of 1 is 0. What is T of x? 1. What is derivative of x squared? That is 2x. What is derivative of x cube? That is 3x squared. And when we put this in a matrix form, we are going to get 0, 0, 0, 0, 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, 0. This is the matrix of T with respect to the standard basis. And clearly what? Determinant of this T is 0 and hence T is not invertible. And easily from the matrix of T with respect to the standard basis, we are able to see that 0 is an eigenvalue. Okay, and this matrix is a nilpotent matrix. In option 3, they have said that there is a basis with respect to which matrix of T is nilpotent. Yes, true. With respect to standard basis, it is a nilpotent matrix. And in option 4, they have said that this is diagonal. Okay, with respect to this basis, it is diagonal. One way of proving this is not diagonal is if you just change the basis. We have basis 1 x square and x cube. From this, if you change this to some other basis, 1 plus x, 1 plus x plus x squared, 1 plus x squared plus x cube. Okay, if you convert from this basis to this basis, this will involve a invertible matrix. Okay, so you can very well multiply this matrix with that invertible matrix C inverse C. That would give you another version of T, which I denoted as T prime. That is going to be the matrix of T with respect to this basis. Either you will have to find this transformation matrix and then multiply that in this way, or you can very well find the matrix with through this itself. T of 1 plus x, that is 1, and T of 1 plus x square, which is 1 plus 2x. Okay, 1 plus x square plus x cube, this is 1 plus 2x plus 3x square. Since the basis entries are lengthy and I am lazy, I am going to call them as v1, v2, v3 and v4. So this is 0 v1 plus 0 v2 plus 0 v3 plus 0 v4. So this is 1 v1 plus 0 v2 plus 0 v3 plus 0 v4, and this would be, okay, first of all I need 2x. So x is appearing, x and constant are appearing in the v2. So let me first fix 2v2. When I put 2v2, instead of 1 plus 2x, I have 1 extra which has to be subtracted from it. So minus 1 times of v1 plus 0 v3 plus 0 v4. Okay, here the highest coefficient is x square, which has highest term is x square, which has the coefficient 3. So with v3 I'll have to multiply 3. Okay, so I will have 3x square, 3x and then 3. Now from 3x I'll have to reduce it to 2x. So I'll have to subtract 1x. X and constant are appearing in v2. So how many times I should subtract it? only one time. So minus V2. Okay, now this x term is balanced. Now from this 3v3 I got 3. Here I reduced 1. So from 3 it is now 2. And I will have to reduce one more. So minus v1 plus 0 v4. If I write the matrix with respect to this basis, what am I going to get? 0 0 0 0 1 0 0 0 minus 1 2 0 0 minus 1 1 3 0. Again then it is a nilpotent matrix of order 4. Hence the minimal polynomial of this matrix is not equal to x. Hence T is not nilpotent. Sorry, T is not diagonalizable. Option 4 is false. Moving to the next question. Here we have a set of matrices and they are asking which of the following are diagonalizable. Okay. In order to check whether a matrix is diagonalizable or not, what are the things that we have in our mind? Like what are the techniques that is available to us? If the minimal polynomial of any matrix consists of linear factors, then the matrix is diagonalizable. This is one thing. And algebraic multiplicity of any eigenvalue is same as that of the geometric multiplicity, then the matrix is diagonalizable. Okay, these two are the ideas that we have. Okay, for the first matrix, what are the eigenvalues? Since it is an upper triangular matrix, 1 4 6 are the eigenvalues, and if an eigenvalue is appearing only once, then the characteristic polynomial is same as that of the minimal polynomial and it will have only linear factors. Okay, distinct linear factors, and hence it is diagonalizable. Okay, and if you look at the matrix that is given in option 2, it is a block diagonal matrix. So in order to find the characteristic polynomial of block diagonal matrix, we can find the characteristic equation blockwise. So first one is x square plus 1 and second is x minus 1. Okay, here your eigenvalues, okay, eigenvalues are lambda is equal to 1, iota and minus iota. Here iota and minus iota does not belong to R. So over R we cannot talk about the diagonalizability of this matrix. If the eigenvalue is not present in the field over which we are talking about the diagonalizability, then the matrix cannot be diagonalizable. Okay, and we have option 3. Okay, here how to check whether this is diagonalizable or not? Yes, you can very well you can make use of the idea that observe this matrix is a symmetric matrix. Okay, when you have a real symmetric matrix, it is very well diagonalizable. Okay, using the simple property you can conclude this is diagonalizable. And option 4, it is a non-zero nilpotent matrix. A non-zero nilpotent matrix is not diagonalizable. That's it. Moving to the next question. Here it is said that A is some matrix given and the quadratic form is defined in this form. Then we will have to check these entries. Okay, so here let us start with it. Okay, the matrix, it has two positive eigenvalues. All the eigenvalues are positive, so they are basically talking about the eigenvalues of this matrix in the first two options. Let us try to identify the eigenvalues as it is or some relation involving eigenvalues. Let me try to find out the trace of this matrix. What is the trace? That is 3 plus 2 plus 1, which is 6. And what is the determinant of this matrix? that is 3 times of 2 minus 6, sorry 2 minus 9 minus 1 times of 1 minus 6 plus 2 times of 3 minus 4, which is minus 21, it is plus 5, and this is minus 2. So basically it is minus 18, isn't it? We have determinant of A is minus quantity. Okay, since this is a 3 by 3 matrix, lambda 1, lambda 2, lambda 3 be eigenvalues of A. Determinant of A is what? Lambda 1, product of the three things. Okay, this product of three things is minus 18, which means all lambda j's are negative. If you multiply three negative values, we will end up in a negative value, or one of lambda j is negative, the rest two are positive. So we have two options. If the first one is removed, then we can pick the second one, and hence first option, that is A has exactly two positive eigenvalues, is true. From this itself, it is clear that all the eigenvalues of A are positive, that is wrong. So option 2 is removed, omitted. Okay, and with determinant we come to this one. Okay, now we'll write down the trace, that is sum of lambda 1, lambda 2, lambda 3, which is 6. If all are negative, then this will not be satisfied. At least one has to be positive, and it has to be bigger than the sum of other two things, so that it is positive quantity. The trace is a positive quantity. So this cannot be possible. So this is not possible. So we are left with the possibility that this. So A has exactly two positive eigenvalues is true. Okay. Now let us evaluate this quadratic form. Okay, that is x transpose Ax. You just use this one. What is Ax? That is lambda x, right? So x transpose lambda x. Since lambda is an eigenvalue of okay, if you want, you can have it as lambda j. Okay, here for any x in R3 we'll have to take. Okay, option 3 and 4 claims. Option 3 claims that it is semi-positive definite, and option 4 claims that the quadratic form is negative for some x in R3. Okay, so what am I doing is that, okay, here we had what? 3 eigenvalues. Okay, lambda 1, lambda 2, lambda 3. Out of the 3, 1 is negative. That is what we just proved. Okay, without loss of generality, take lambda 1 as negative eigenvalue. Okay, the order in which we write doesn't matter. That is why I am choosing lambda 1 as the negative eigenvalue. Then there exists a non-zero x in R3 such that Ax is equal to lambda 1x. Okay, for this x, what is our quadratic form? Q of x is x transpose Ax, which is nothing but x transpose lambda 1x. Since lambda 1 is a scalar, you can take it out. So lambda 1 x transpose x. This is always a non-negative quantity, right? Since x is a non-zero vector, this is a positive quantity. Okay, since x is not equal to 0, this x transpose x is positive. Okay, therefore what is q of x? It is negative, since lambda 1 is negative. So we are able to identify one such x for which the quadratic form is negative. So option 4 is true. When option 4 is true, of course option 3 is false, because option 3 claims for all x in R3 the quadratic form of x, that is q of x, is non-negative. That is false. Now we move to the next question. Here in this question they have given a matrix, okay, and based on the matrix we have some options. Okay, what are the options? First option says that it has 0 as an eigenvalue for some x. Second option says 0 is not an eigenvalue for any x. Third option says a of x has eigenvalue 0. 0 is one of the eigenvalue for all x. And fourth option says that it is invertible for every x. So I think option 2 and 4 are if and only if kind of a thing. If you prove option 2 is true, then automatically option 4 is also true, and vice versa, right? Okay, first of all we'll evaluate the determinant of this a of x. What is that? 1 plus x square into 2x into 13, that is 26x minus 68 minus 7 times of 39x minus 32x plus 11 times of 51x minus 16x squared. So it is 1 plus x. I can multiply it inside. 26x minus 68 plus 26x cube minus 68x square minus 7 times of 7x. So it is minus 49x plus this is 561x minus 176x squared, and when we simplify it, what we are going to have is 26x cube minus 244x square plus 528x minus 68 equals 0. So that, sorry, not equal to 0. This is the determinant. Basically determinant of a of x is a what? This is a cubic equation. So what do we mean by a cubic equation? Polynomial of degree 3. So it is basically a polynomial of odd degree, which ensures determinant of a of x has at least one root x in R. Okay, let me call that root as x prime. That is determinant of a of x prime is 0. When the determinant is 0, okay, we are having this determinant is 0, and this a of x is a square matrix, so it will have 3 eigenvalues. Let us name them as lambda 1, lambda 2, lambda 3, and we know determinant of this is product of these things, right? If the determinant is 0, which implies 1 of lambda j must be 0. That is what option 1 says. Okay, option 2 claims that 0 is not an eigenvalue of a of x for any x, but I have identified one element in R for which the determinant is 0, and then 0 is one of the eigenvalue, therefore option 2 is wrong. When option 2 becomes wrong, option 4 also becomes wrong, because for this x prime, if you substitute this x prime in the entire a of x, your matrix is not invertible for this x prime. Okay, and option 3 says that a of x has eigenvalue 0 for all x in R. No, it has at least one root in R, and at most I can say there are 3 roots in R. So to the maximum for 3 values of R only, this will have 0 as an eigenvalue. Minimum for one value, it will have 0 as an eigenvalue. But for all, that is not true. Right? Now we move to the next question. Here it is given that m, n, r are natural numbers and A is any m by n matrix with real entries, and it is satisfying a property that when we multiply A with its transpose and we are raising the power to R, we are getting the identity matrix. Okay, and I is given to be a m by m identity matrix, and what is A transpose is explained, and what can we conclude from these informations. This is the question that we have. Okay, so okay, from which let us try something. First of all, we must try and identify one such A with which, if it is possible, let us try to discard some options. Right? So let me. Okay, I think there is no need of discarding the options. Given A is of order m by n, then A transpose will be of order what? N by m. So of course when we make a product of these two things, it will be of order m by m only. Okay, and this quantity is equal to identity matrix, and clearly it is said that A is a matrix with real entries. Clear? It is a matrix with real entries. And when we take the determinant of this quantity is identity. Okay, this may be written as since this A transpose is a square matrix, we can write it as determinant of A transpose multiplied with determinant of A transpose till determinant of A transpose is equal to 1. This is repeated R times. Since the discussion is taking place in real numbers, this claims that determinant of A transpose is not equal to 0, which tells us A transpose is invertible. Okay, fine. And it is very well possible to find out A transpose A also. But will it be invertible? It is a matrix of order n by n. Now option 3 claims for fact that A transpose A is also invertible. So from which what A transpose A can also be found, it is n by n. Okay, and yeah, will it be invertible? In order to claim this will not be invertible, I am considering a matrix 1 0 0 0 1 0 as my A. Okay, and my A transpose is 1 0 0 0 1 0. When I find A transpose, it is 1 0 0 1, which is 2 by 2 identity. Yes, this is a matrix of order 2 by 3 and this is of order 3 by 2, hence it is the case. And when I find A transpose A, I would get a 3 by 3 matrix, right? So A transpose A 1. So this one with this one, this one with this one, and 0 1 0, and when I go with this one, no. So I am able to identify one such matrix A of order m by n, and A transpose to power R. Here R is 1. 1 is also a natural number, right? So the hypothesis is satisfied, but A transpose A, which is not invertible. Hence option 3 is false. In order to satisfy the hypothesis, I don't need my m and n to be equal. That also I have checked, right? I am able to produce some rectangular matrix with which I am able to prove the requirements. Yeah, good. Now, what am I going to check? If m is equals n, if m equals n, this is assumed, with which we'll have to prove this one. Then we'll have to claim A is invertible. Okay, so in this case, when m and n are equal, this determinant of A transpose, which is not equal to 0, we claimed it, right? So this may be written as determinant of A product with determinant of A transpose, which is non-zero. This very well tells us that determinant of A is also non-zero and hence A is invertible. Option 4 is also true. Okay, we move to the next question. A is given to be any n by n real matrix such that A square equals A. Okay, then which of the following are true? This is the question, right? Okay, so I think we have worked this problem in one of the previous videos. So let me just give you the hint. If this is given, then with which what you can do is that you can very well take down an annihilating polynomial. Okay, that is x square minus x, so x into x minus 1. So any polynomial which annihilates the matrix A will be divided by the minimal polynomial. So with which what we get is minimal polynomial of this thing can be either x or x minus 1 or x times of x minus 1. Okay, so from this itself it is clear that eigenvalues of A are either 0 or 1. Yes, true. If this is the minimal polynomial, then what we get, minimal polynomial will also annihilate the given matrix. So my A will be either 0 matrix if x is the minimal polynomial, or A will be the identity matrix if x minus 1 is the minimal polynomial. Then if not, my A will be similar to something of this form. This is what we proved in one of the previous videos. Okay, since this is the, if this is the minimal polynomial, then what happens? Then my characteristic polynomial will take the form x power m, okay, and x minus 1 n minus m. So I will have m by m and n minus m by n minus m block, which will have 0 in the diagonal entries and this will have 1 in the diagonal entries. Okay, so this is what A is similar to one such matrix, right? Okay, so what? So from this, if you find out trace of A which is same as that of n minus m, which is the rank of A. Okay, and from this you can very well identify what is identity minus A, and you see the rest of the things going to happen. So option 3 and 4 are true. Now option 2, that has some twist in it. A is itself a diagonal matrix with diagonal entries 0 or 1. This is what they have said. Okay, A itself is a diagonal matrix. That is what they have said. But that need not be true always. Okay, if you choose A to be 1 A 0 0, okay, what is A square? It is 1A with this 1 0, so that gives you 1. 1A with this A0, it is A. 0 0 with 1 0, 0 0 0 with A0, 0. So A square you are getting it as A. This A can be any real number. I don't impose anything on it. This can be any real number. But your option 2 claims that it has to be a diagonal matrix, but the matrix that I consider is not a diagonal matrix. It can be treated as a upper triangular matrix, but it is not a diagonal matrix. Clear? So A need not be a diagonal matrix. Of course, in the diagonal we have zeros and 1 only, but it is not a diagonal matrix. Hence, option 2 is wrong. Okay. Moving to the next question. Here, it is for any square matrix B, n of B is given to be the collection of vectors in Rn such that Bx is 0. So, basically, the null space of B is defined. Right? And AB any 4 by 4 matrix with dimension, these things are happening. Okay. So, here, this is given null space of A minus 2i is 2, which means my GM of lambda equals 2 is smaller than or equals AM of lambda equals 2, and from this what I get is GM of lambda equals 4 is smaller than or equals AM of lambda equals 4. Okay, now I'll have to identify the eigenvalues. Eigenvalues of A. Since this dimension is 2, okay, dimension of A minus 2i is 2, the 2 is repeated 2 times. Okay, and from this I get my 4 is repeated 1 time. Okay, A is a 4 by 4 matrix. I need one more eigenvalue. Okay, how to find it? For which we use the result that rank of a matrix A is bigger than or equals number of non-zero eigenvalues. Okay, here rank of A is given to be equal to 3. So this 3 has to be bigger than or equals number of non-zero eigenvalues. So till now we have found 3 non-zero eigenvalues. Hence the remaining eigenvalue must be 0. Okay, therefore 0, 2 and 4 are the eigenvalues. Since 0 is one of the eigenvalue, determinant has to be equal to 0. Okay, and what? Okay, coming to the diagonalizability, here AM of lambda is equal to 2 is 2 and GM is 2. Therefore, the AM and GM are same, right? Hence, the matrix has to be diagonalizable. Claiming it is not diagonalizable is wrong. And eigenvalues are 0, 2 twice and 4 once. Therefore, the trace is 8. That is right. The next question is, H is given to be a real Hilbert space and M is some closed linear subspace of H. Okay, and x0 is some point in H minus M. And actually, if you try to visualize what is happening here, you can have this as your H, and inside which you have something called M. Okay, you are identifying a point x0 in H minus M. So somewhere here you are identifying a point x0, and you will have to identify a point y0 in M such that norm of x0 minus y0 is infimum of norm of x0 minus y, where all the M is taken from here. So y0 would be somewhere here. Okay, so this is what is given, and we will have to study about that y0 and the relation between x0 and y0. This is what we are going to do, right? So what is basically given? Given that norm of x0 minus y0 is equal to infimum of x0 minus y such that y is a member of M. Okay, so this norm of x0 minus y0 is infimum of all the quantities. Therefore, if you compare an arbitrary quantity like this x0 is a fixed value, right? So this y naught and y are the things that we are discussing from M, and since M is given to be a closed linear subspace, this y naught is also a member of M. Fine. For this y naught, when you have that y naught there, that is the infimum. If you choose some other y, that will be the bigger quantity. So this trivially tells us that norm of x naught minus y naught is smaller than or equals norm of x naught minus y. Okay, this is true for all y in M. So this y naught is called the point of best approximation to x naught from M. Okay, so from this, let us state a result here. Let V be an inner product space and let X be a member of V, and let W be a subspace of V. Then U is a point of best approximation if and only if this x minus u comma w equals 0, inner product of x minus u comma w equals 0 for all w in w. Okay, now so we have the best approximation to x naught, and that is what we are denoting it as y naught. Okay, now in option 1, what are they doing? They are asking for the uniqueness of that y naught. Okay, suppose there exists y1, y2. Suppose there exists y1, y2 which are best approximations to x naught from M. Okay, then what can we write? This x naught minus y1 comma for y equals 0 for all y in M. Okay, and similarly x naught minus y1 comma y2 comma y equals 0 for all y in M. Okay, in particular x naught minus y1 comma y1 minus y2 is 0, which is same as that of x naught minus y2 comma y1 minus y2. Why? This y1 and y2 are points which are taken from M, and M is a closed linear subspace, hence y1 minus y2 must also be a member of M. And the results that we have written here are true for all the entries of M. That is why we have written like this. Okay, and in order to claim these two are equal, what shall we prove? They are one and the same. In order to prove one and the same, let us evaluate the norm y1 minus y2. Okay, by the properties of inner product, this is norm y1 minus y2 square is inner product y1 minus y2 comma y1 minus y2. I just add and subtract the quantity x naught in the first position. So this is what y1 minus x naught comma y1 minus y2 plus x naught minus y2 comma y1 minus y2. Using the properties of inner product, you can write this as minus x0 minus y1 comma y1 minus y2 plus x0 minus y2 comma y1 minus y2. So if you mark this as equation 1 by 1, this is 0. So this implies y1 minus y2 equals 0. From this, y1 is equal to y2. This proves such best approximation is unique. Okay, and in option 2 they are claiming this x0 has to be perpendicular to m. Is that so? Is that so? It means this x0 inner product of this x0 with any entry of m should be equal to 0. Here let us consider an example. Okay, let me consider this R2 as an inner product space here, and the m that I consider is the positive axis. Okay, I am arbitrarily choosing some point from this m, that is half comma 0, and I am choosing some point which is in h minus m, that is R2 minus m. Okay, if I take the inner product of these two things, which is simply half, that is not equal to 0, hence these 2 points need not, like the point x0 is not perpendicular to my subspace m. So option 2 is false. Option 3 claims that that y0 is perpendicular to m. This y0 is also a member of m. Okay, this y0 is also okay. The third one I am doing, y0 is a member of m, and this y0 is perpendicular to y0 is possible only when y0 is 0 vector, because no element is equal like orthogonal to itself. Okay, so it means what? Inner product y0 comma y0, it has to be equal to 0 in order for that y0 to be orthogonal to y0. But this is norm y0. Okay, norm is 0 means that element has to be equal to 0. That is what I have written. So this is also not true in general. Okay, this x0 minus y0 is orthogonal to m. That is what we have written here. Okay, x0 minus that point is orthogonal to all the, like when you make the inner product of x0 minus y0 with all the elements of m, you are getting it to be equal to 0. That is what option 4 claims. Therefore option 4 is true. That's it. Thank you.